This is Properties of Shape, Part 1, Isosceles Triangles within Circles. Now before we look at that, we need to remind ourselves of some angle properties. In the blue diagram, we have angles on a line, and these add to 180. So we can draw this arc round, if we like. Remind ourselves that gives us a semicircle, which is 180 degrees, and any number of angles that are within this semicircle will add up to 180. In the red diagram, we've got vertically opposite angles are equal. So that means the star in the top is the same angle as the star in the bottom. Likewise for the left and the right hash. A very important one is in the orange diagram where we've got angles inside a triangle adding up to 180 degrees. You must remember that. In the green diagram, we have alternate angles are equal. Now this is when you've got this sort of Z shape indicated also by two parallel lines. You must have these indications of being parallel with the arrows there. And the two corners of the Z are equal angles. And finally, in the black diagram, corresponding angles are equal. Again, this is in this F shape, indicated also with two parallel lines with the arrows. And again, the angles at the corners are equal to each other. We also need to know about a couple of triangles in particular, the isosceles triangle and the equilateral triangle. In the isosceles triangle on the top here, we have one line of symmetry coming down the middle. That's because we've got two sides the same length on the left and right, and also two angles the same size in the bottom two corners. In the equilateral triangle, we have three sides the same, and three angles the same, and also three lines of symmetry. Each angle is worth 60 degrees because 180 divided by 3 is 60. So, isosceles triangles within circles. If we have A and B here, then that gives us a chord. Now, we need to know about that word, but usually, even if we didn't know, we'd still be able to understand what to do. If we draw two radii coming out from the centre O, out to A and out to B, then this creates an isosceles triangle. And we know it's an isosceles triangle because we've got a radius there and a radius there. And this can also be split into two right triangles, there and there. An example, let's fill in the missing angles inside this triangle. So again, we're going to make use of the fact that we know this is an isosceles triangle. And therefore, we've got left and right being the same, so 40 degrees is also in here. Now we've got 40 plus 40, that's 80. And 180 is the full triangle's degrees, so that leaves us with 100 for this angle up the top. Example 2, this time we've got the angle up the top, using our symmetry line again. We have the angle at both corners being the same as each other. So we've got 180, take away the angle at the top, which is 110, that leaves us with 70, and that 70 needs to be split equally. So that's 35 degrees in the two corners at the bottom. Now we'll also be looking at some questions which involve Pythagoras. A reminder of Pythagoras here. We need to use Pythagoras when we have a right angle triangle and we're given information about the lengths of two sides and we want the third side. So if we're looking for the longest side, which is always across the right angle, then we square the two shorter sides, add them, and then square root. If we're looking for one of the shorter sides, we square them two sides, subtract them, and then square root. an example here. Calculate the length OB. So, since we've got an isosceles triangle, again it can be split into two right angled triangles. Now I've got that on the diagram already. Let's take this triangle out of the diagram. Now, since 16 is A to B, then B to C is 8, because that's half, and we know this because it's symmetrical. The green line is a line of symmetry there, and it splits it into two. So we've now got 6 on the green line and 8 on the blue line, and we're looking for red, which is OB. So that's the hypotenuse, so we need to use the adding version of Pythagoras. 6 squared plus 8 squared, that's 100, and then square root, that's 10 for OB. Example 2, let's calculate the length OC. So again, we've got the isosceles triangle, which can be split into two right angled triangles. We've got AB, which is 24. Again, splitting it down the middle means that we've got CB as 12. And then drawing this triangle out separately, you can see that 13 is on the hypotenuse, 12 is one of the shorter sides. So that means we're going to be using the subtract version of Pythagoras to work out the length of OC, which is another shorter side. So 13 squared minus 12 squared, that works out at 25, and square root, that's 5.